Okay, in this session, we'll look at the second part of chapter 6. We'll look at, or continue looking at, normal distributions. We'll talk about the normal approximation to a binomial distribution, and we'll also talk about sampling distributions. Okay, I'm gonna go to the shared screen, and we're gonna pick up from where we left off. The last time we were talking about the standard normal distribution. And in the standard normal distribution, the mean mu is 0 and the standard deviation is equal to 1. We looked at the fact that area is probability and probability is area under the curve. The total area for this standard normal distribution curve is 1. Remember the last time we used the lowest end point is -10. We used the uppermost end point is +10, and we're able to use a calculator and the normal CDF function to find the area. Here's an example. Okay, here we have problem number 9, and I'm just going to generate a similar question. Right, and we're asked to basically find the probability that a given score is less than -1.46. We're asked to draw a sketch, and then we're also asked to find the probability. So first off, we're finding the area to the left of -4.6. So my correct graph here would be B. We're finding the area or the probability to the left of -1.46. In order to find that area or the probability, I'm going to pull up my graphing calculator. I want to go into distribution, and I want normal CDF. Once I select normal CDF, I'm going to put in my interval. So notice that for the standard normal curve, it runs from -3 to +3. But as we talked about, this curve keeps on going infinitely. So instead of using -3, I'm going to use -10, right? And that would account for all of the area to the left, comma, -1.46. And I can calculate that area or that probability as 0.0721. So I'm going to enter that in. All right, and we have the area, which is the probability. All right, I'm going to go back to our slides for just a second. And we're going to talk about converting from, or rather I should say converting to a normal standard distribution. All right, so here we're given a non-standard normal distribution. And what a non-standard normal distribution is, it's still a distribution, has the bell-shaped curve. However, its mean is not 0. Its mean can be some other value than 0. And the standard deviation is not 1. Okay? The standard deviation is some value other than 1. However, we can standardize by using this formula. Z, right, which is the z-scores, which we were working with in that previous problem, right? The z-score was -1.46, and we found the area to the left of the z-score. From the standard normal distribution, just recall that the z-scores run from -3 to +3. So in essence, we'll be taking a non-standard normal distribution, and we would be standardizing them by using this formula. Z equals 2, and once again, Z is z-score, X, and X would be your given value, minus mu divided by the standard deviation. All right, so taking a look at that once again, Z is equal to X minus mu divided by the standard deviation. Whenever we are calculating z-scores, we always round z-scores to 2 decimal places. We can also take this formula and we can solve it for X. For example, if we're given an area or a probability, and we're asked to convert that area or probability to a z-score, we can actually take this conversion formula and we can solve it for X. So here's how that looks. I'm going to return to the document camera. So in our document camera, we have Z is equal to X minus mu divided by the standard deviation. We can actually solve this for X. We can solve this for X by multiplying both sides by the standard deviation, and we could add mu to both sides. So that formula will look something like this. X is equal to the z-score times the standard deviation plus the mean. All right, so here are the two formulas involving z-scores. All right, so let's take a look at this very first formula. I'm going to go back to our shared screen. And I'm actually going to pull up a problem from the homework. We're going to take a look at problem number 18. Okay, sorry, my computer's running a bit slow. Okay, eventually I'm going to find problem number 18. Okay, here we have problem number 18. And in problem number 18, we're asked to find the area of the shaded region. And the problem reads as the graph to the right depicts IQ scores of adults. and those scores are randomly distributed with a mean of 100 and a standard deviation of 15. Okay. And we look at this bell-shaped curve, and notice that I'm not actually seeing a z-score, right? They actually are giving us 110, right? We're given the mean, we're given a standard deviation. We can actually convert 110 to a z-score. So to see how that's done, I'm going to return to the document camera. So we were given a value of 100. So this is to convert to a z-score. So we were given the value 100. Excuse me, we were given the value 110. Recall that the mean was 100. So in our z-score formula, it was x minus mu. So that's 110 minus 100 divided by the standard deviation, which is 15. So on the numerator, 110 minus 100 is 10 over 15. And then once we convert that to a z-score, remember that for our z-scores, we rounded 2 decimal points and we get 0.67. So now in our calculator, let's push that up so you can see that. We're not going to use 110, we're going to use 0.67. So we're going to find the area from -10 to 0.67, and we're going to use that normal CDF to find that area or that probability. Right, so if I return to our shared screen, all right, so in the calculator, I'm going to pull up the normal CDF. And remember, we've converted 110 to a z-score of 0.67. So I'm going to put this in my calculator as the normal CDF from -10 to 0.67. And we have an area of 0.7486. All right, so we've converted 110 to a z-score, and then we use a normal CDF. We'll also take a look at problem number 20. All right, so in problem number 20, we're asked to, once again, find the indicated IQ score. Right, so notice we're given X as our variable, and X is what we want to find. The graph depicts IQ scores of adults. These scores are normally distributed with a mean of 100 and a standard deviation of 15. Right, so notice I'm given that the area or the probability is 0.6, and I actually want to convert that area to a z-score. So if you remember the second formula we had X was equal to the z-score times the standard deviation plus mu. So how would I find the z-score? So keep in mind, in the last section, we found z-scores by using the inverse normal. And just remember, for the inverse normal gives us the area to the left. Okay. So keep in mind here that our area is 0.6. So I'm going to go back to our document camera for just 1 second. All right, so notice our answer is 103.8, but we'll see how that 103.8 was determined. All right, so back to our document camera, we had x is equal to the z-score times the standard deviation plus mu. So remember, for our z-score, we're going to use the calculator function, which is the inverse normal, or the inverse norm, and that area is 0.6 times our standard deviation, which was 15, plus the mean, which was 100. All right, so this calculation should give us our IQ score. So I'm going to put that into the calculator. I'm going to switch screens here for just 1 second. So I'm going to put this in as the inverse normal. So I'm going to go into distribution, inverse normal, 0.6. I'm going to close off my inverse normal function, times the standard deviation, which was 15, plus mu, which is 100. So notice, once I perform my calculation, I have 103.8. All right, so now we're going to return back to the slides, and we're going to look at the normal approximation to a binomial distribution. All right, so this is the normal distribution as an approximation to a binomial distribution. And there's just two conditions in order for you to be able to take a normal distribution and approximate it as a binomial distribution. The first requirement is that the sample is a simple random sample of size n from a population in which the proportion of successes is p, or the sample is the result of conducting n independent trials of a binomial experiment in which the probability of success is p. Next, n times p must be greater than or equal to 5. And n times q, remember that q is 1 minus p, it has to be greater than or equal to 5. Whenever we use a normal distribution to approximate a binomial distribution, keep in mind that a normal distribution uses continuous random variables and a binomial distribution uses discrete random variables. So whenever we use the normal distribution to approximate a binomial, we must use what's called a continuity correction. And here's that continuity correction. You would either subtract 0.5 to your value, or you would add 0.5 to your value. Here are some examples, right? So here are the examples if you are approximating a binomial with a normal. So it says at least 152, which would include 52 and above, we would use 151.5. All right. More than 152, this does not include 152, so you would add 0.5. So we would find the area to the right of 152.5 instead of 152. At most 152, that would include 152. So we would look at the area to the left of 152.5, right? Because that would include 152. Fewer than 152, which doesn't include 152, you would find the area to the left of 151.5. And if you wanted to find the probability of exactly 152, you would actually find the area between 151.5 and 152.5. So this continuity correction, you're either going to add or subtract 0.5. So let's take a look at an example. We'll take a look at example or problem number 29. So give me just 1 second to actually navigate to problem number 29. All right, problem number 29. All right, so in this problem, we're given the conditions that n times p is greater than or equal to 5, and n times p is greater than or equal to 5, and n times q is greater than or equal to 5. And I'm just going back to check something, okay. We want to estimate that p is fewer than 4, with n being 13, so n would be the number of trials, and p is equal to 0.4, that would be the probability of success, right? So this would, in fact, allow us to approximate this binomial as a normal. So it says by using the normal distribution as an approximation to the binomial, if n times p is less than 5 or n times q is less than 5, then state the normal approximation is not suitable. All right, so first of all, let's check the conditions. N times p. Well, notice that n is 13 and p is 0.4. So if I were to multiply those two together, 13 times 0.4, I get 5.2, right, which is greater than 5. If I were to multiply n times q, so remember that q is 1 minus p, so q would be 0.6. 13 times 0.6, again, is greater than 5. All right, so we can approximate this binomial as a normal. We're asked to estimate the probability fewer than 4. Okay. So we're gonna have to do a couple of things here. We're gonna have to find, in order to use our z-score, right, z is equal to x minus mu divided by the standard deviation, right? We have x, right? We're basically gonna use x as 3.5, and we'll see why we're using x as 3.5 in just a second, minus mu. So remember that the mean of a binomial distribution is n times p, We also need the standard deviation. So the standard deviation of a binomial distribution is the square root of n times p times q, right? So before we began using the normal CDF function in our calculator, we have to find a few things. So I'm going to go back to our document camera. And the first thing we're going to do is we're going to find the mean. Okay. So I'm going to write the values down. So just looking back at the problem, n was equal to, give me 1 second. N was equal to 13. P was equal to 0.4. And Q, which is 1 minus P, which is 1 minus 0.4 equals to 0.6. Okay, so these are the key pieces we're going to need for our calculation. So if we were to calculate the mean is equal to n times p. So I want to multiply 13 times 0.4. And once we multiply 13 times 0.4, I believe we get 5.2. The standard deviation of a binomial distribution is the square root of n times p times q. So that's the square root of 13 times 0.4 times 0.6. And if I put that in my calculator, we have 1.76. So that's the second step. Let me actually write that out. We would find the standard deviation. And in the third step, we're going to find the z-score. So remember, the formula for the z-score was x minus mu divided by the standard deviation. So our x value, we're finding the probability fewer than 4, so we must use that continuity correction. So I'm going to subtract 0.5. So I'm going to use 3.5 minus mu, which is 5.2, divided by the standard deviation, which is 1.76. So if I calculate that using my calculator, I have a z-score of negative 0.97. So bring that up so you can see. All right, so we have 0.97. So next we will calculate the probability. All right, so now I'm going to return back to our shared screen. I'm actually going to do the calculations with the calculator. Okay, just showing, working that out by hand. All right, so the first thing I'm going to do is calculate the mean. So once again, the mean was 3.5 minus 5.2. Okay, I'm gonna do things a little bit differently because I'm not gonna round anything. I'm gonna let the computer handle all of the calculations, and I'm gonna round last. So I put in 3.5, excuse me. I wanna put in n times p. So I have 13, which is n, times 0.4, right? And we have our 5.2, which was our mean. I'm gonna store that for A. So I'm gonna hit STO, which is store. And notice that A is above math and it's green. So I'm gonna hit alpha in math and I'm gonna hit enter, right? So the calculator has stored 5.2 for A, which is our mean. Next, I'm gonna enter in the standard deviation. So remember, the calculation for the standard deviation is the square root of n, which is 13, times 0.4 times 0.6, and I'm going to store that for B, right? So notice here's our 1.76 calculation, right? But this number actually keeps on going. It's an irrational number. And we've stored that for B. Now, in order to calculate the z-score, since we're finding an estimate fewer than 4.5, so if I go back to our slides for just a second, okay, if we look at this fewer than 152, that's finding the area to the left, so we subtract 0.5 for the continuity correction. So here our value for x, for if we take into account the continuity correction, should be 3.5. So in my z-score calculation, we have x, which is not 4, but we're using a continuity correction, which is 3.5, minus the mean, which we stored as A. So in order to recall that, I'm going to hit alpha in math. And we're going to divide that by the standard deviation. So remember, we stored the standard deviation for B. And now I'm going to hit enter. So I have negative 0.962435. So I'm not going to round anything. I'm actually going to use this in my normal CDF. So I'm going to take this z-score, right, because we just performed the z calculation, and I'm going to store that for z. So if I look on my calculator, z is above the 2, so I'm going to hit alpha and 2, which is z. So now I'm going to pull up the normal CDF. Since we're finding the area to the left, I'm going to put in -10. I'm going to put in our z-score. So we're not rounding anything. We're letting the calculator carry out all our digits. And notice we have the probability as 0.1679. So we use what's called a continuity correction. All right, so I'm going to go back to our slides and we'll take a look at the last topics of chapter 6, and it's the sampling distribution of a statistic. And this slide just reads: the sampling distribution of a statistic is the distribution of all values of the statistic when all possible samples of size n are taken from the same population. Right. So here's an example. Right, so here we have a sample. All right, and from that sample, we can find the mean. We can add up all the values and find the mean. If we were to take many samples of the same size, right? Each sample would yield a slightly different mean. However, the distribution of the sample means tends to have a normal distribution. So what does this mean? So let's take for example, the statistics courses. If we were to take all of our statistic courses for a year, and let's say we were to find the mean average for every class. Well, I'm not quite saying that right. If we were to sample 5 students and we were to take those 5 students and let's say we were to find the mean of their final average, right? We would get a value. So let's say we randomly sample another 5 students. We added up all of their test scores, we got the mean. All of those samples would have a normal distribution, right? They would take on this bell-shaped curve. Most of the mean scores would lie at the middle. All right, so how does this actually affect what we're doing? All right, well, we're going to take a look at problem number 29. Excuse me, we're going to take a look at problem number 38. All right, and in problem number 38, we're given the following information. For women aged 18 to 24, systolic blood pressures are normally distributed with a mean of 114.8 and a standard deviation of 13.1. If 23 women aged 18 to 24 randomly selected, find a probability that their mean systolic blood pressure is between 119 and 122. We're asked to round to 4 decimal places. Now notice this problem is a little bit different than all the problems we worked with so far, in that the problems we worked with so far, a randomly sampled person or a single randomly selected color was chosen. Here we're randomly selecting 23 samples. So since we're sampling something greater than 1, this would constitute a sampling distribution. We're asked to find the systolic blood pressure between 119 and 122. So first thing is we're finding the area between 119 and 122, which are non-standard scores. So we must standardize these. We're going to convert both to z-scores, and then we're going to use the Normalcdf to find the area between these 2 z-scores. So I'm going to go back to our document camera for just 1 second. And we're going to convert 119 to a z-score. So notice that we were given that the mean is 114.8. The standard deviation was equal to 13.1. And we're randomly selecting 23 women. Okay. So first thing was we're going to convert 119 to a z-score. All right, so remember our calculation for a z-score. That's equal to x. So I'm not using any continuity corrections or anything. So I have 119 minus the mean, which is 114.8, divided by the standard deviation, which is 13.1. So here's where the sampling distribution comes in. I want to divide my standard deviation by the square root of n. So remember that we're randomly selecting 23 women. So n is 23. So in my z-score calculation, I'm going to divide my standard deviation by the square root of 23. Right? So if I were to put that into my calculator, we should get 1.54 as a z-score. Next, we're going to convert 122 to a z-score. So that z-score calculation was x, which is 122, minus the 14.8, divided by the standard deviation, which is 13.1, divided by the square root of n, which is 23. And once we calculate this, we should have 2.64 as a z-score. So we're going to use a calculator and we're going to find the area between 1.54 and 2.64, right? But we're going to perform the same calculations in the calculator just to make sure everyone is okay with entering into the calculator. All right, so I'm going to go back to our shared screen. All right, so let me start that once again. Okay, so now we're going to return to the shared screen. All right, so I'm going to put in, for that first z-score, for the numerator, I'm going to put in a set of parentheses. So that's 119 minus 114.8. I'm going to close off the numerator, divided by, I'm going to open up begin parenthesis for the denominator, 13.1 divided by the square root of 23. So I'm going to close off my square root function, close off my denominator, and I have my 1.53. I'm actually going to take that value and store it for A. We're going to convert 122 to a z-score. So once again, a begin parenthesis for the numerator, 122 minus 114. As I look back at my notes, that should be 114.8. Close off my numerator, divided by another begin parenthesis for my denominator, 13.1 divided by the square root of 23. Once again, I close off my square root, close off my denominator. I'm going to store that for B. And now I'm going to bring up my normal CDF, and I'm actually just going to find the area between A and B, right? Because the calculator has these numbers stored for A and B. So I'm going to bring up the distribution, normal CDF from A to B. And once we round, we have 0.0579. All right, thanks for watching.